Hello, everyone. With Governor Cuomo's announcement, um, I'm finding I'm going to be doing a little slightly different setups for these, since we're going to be finishing up our year doing it this way. Um, I have mixed emotions about that. But regardless of it, this is your friendly heavy physics teacher. And here I am with a lesson for my college physics group. This may or may not become a lesson for my Regents physics, depending on how eager they might be to get into this. But this is something that I need to cover for the college physics group because this is part of the curriculum from Siena College. Okay, so we're going to be looking at geometric optics, specifically mirrors and curved mirrors in particular. And this is for Unit 11, Lesson 3. Okay, first off, some vocabulary. You need those notes. You need that note sheet. Okay, so some nomenclature that I'm going to be using a lot of. All right, first off, object. Object is the thing that is going to be looked at. All right. All of these books are objects. All right. And I can put a book in front of a mirror and you can see that book in the mirror. Well, the book is the object and the replica of it in the mirror is the image. Okay. So object, the thing that's going to be we're making a optical reproduction of. Image is the actual optical reproduction of that object. It's going to look the same. It may be different in size. It may be different in proportion. And all of that is due to the optical device making the image. Okay. Focal length. Script F. Focal length is the distance that the optical device will focus reflected in the case of a mirror or refracted in the case of a lens light to a point. Okay. um, uh, when I start doing my diagrams, that'll make more sense. Okay. Object distance is the distance the object is away from the device. Image distance is the distance the image appears to be from the device. It might be real or it might be virtual. And there's the other two key vocabularies points for geometric optics. Okay. Real image. A real image can appear in real space. Okay. You can project it onto a screen, and on the screen could be a sheet of paper, it could be a movie screen, it could be the wall, but some flat thing, you can project the image onto it and you can recognize the image as being a reproduction of the object. Okay. Real image means that the image can be produced in real space. A key, a real image is always inverted in its orientation compared to the object. So if we were looking at my hand and then we were looking at a real image of my hand, it would appear upside down. It would appear upside down. Okay, inverted. Left would invert to right. Okay, so everything is inverted. Real image. Virtual image is an image that will only appear inside, quote unquote, or behind, quote unquote, the device producing the image. So the only way to see a virtual image is to be looking into a mirror or to be looking through a lens back at the object. Um, so virtual image, you cannot project it onto a screen anywhere in real space. and the image will always be upright. In other words, its orientation is the same as the object. Okay? So in other words, when you look in a mirror in the morning, because it's a plane mirror, you're looking at a virtual image. The only way to see that image is to look into the mirror. All right? Okay. Now, geometric optics means that there's going to be a refocusing of the light due to a change in shape from being flat. Okay? For mirrors, we create a curved shape. And if the curve is on the inside, we call it concave, a concave mirror. If the curve is on the outside of the bowl that would be created by the mirror, if the curve is on the outside, it's called convex. All right? Okay, these equations are true whether we're using a mirror, whether we're using a lens, whether we're using a concave or convex mirror, whether we're using a convex or concave lens. These hold true for all optics situations, and I will use them later on in this lesson to illustrate how we can calculate how far away the image might be. Or if we know where the object is and we know where the image is, we can calculate the focal length of the optical device. This equation down here is called the magnification equation. M is the magnification factor, and SI over SO is the ratio of the size of the image to the size of the object, and that is equal to the ratio of the image distance to the object distance. The negative sign here tells us whether the image is going to be inverted or upright. If the image distance is positive, and you have the negative sign here, that means the size of the image will be inverted. That means it must be a real image. Make sure you check the notes out that all of this are part of. Okay, for the remainder of this lesson, we are simply going to be talking about curved mirrors. And we're specifically going to be talking about spherical concave mirrors. And for spherical concave mirrors, or spherical convex mirrors, the focal length is always equal to 1/2 of the radius of curvature. Or you could think of it as the focal length is half the distance from the center of curvature to the lens, to the mirror. Okay? Now, there's a problem with spherical concave mirrors. They have this defect known as spherical aberration. And all that means is that a spherically shaped reflector cannot precisely focus the light onto a single point. All right? So to get around that, instead of using a spherical shape or the part of a sphere, they use a parabola. All right? And all of the reflecting systems that are used, whether it's a radar telescope, whether it's a light telescope, whether it's a radar satellite dish, whether it's a radar reflector, whether it's the light reflector that is in a headlight of a car, they always try and shape it according to a parabolic shape rather than a spherical shape. But if worse comes to worse, you can use a sphere and you can get pretty good reflection and image production from a spherically shaped mirror. Okay, now I need you to get out the worksheet that says mirror diagrams. And it's going to have something that looks like this as the first diagram on it, okay? Except instead of a candle, it's got an arrow, all right? We're going to be doing mirror diagrams for the next couple of minutes, and I'm going to be doing them real time rather than stop motion to show you how the rays of light travel to the mirror and then get reflected and then get focused so that they produce the image. So you're going to need two things in front of you for this next part of the lesson. One, the worksheet. You're going to need a ruler to do the worksheet. Okay? Next to that, have the diagram rules, the optics diagram rules, which tell you if a ray is parallel to the principal axis, it gets refracted or reflected through the focus point. If a ray is passing through the focus point on its way to the optical device, it gets reflected or refracted parallel to the principal axis. That rule sheet you need to have out as well. So while I'm making my change here, pause and get that stuff out, get your ruler, get a pencil, get ready to go. Okay, hopefully this doesn't go crashing down onto the floor on me. This easel here was used by my wife way back when she was doing her art school stuff. And so I actually had to run out to the local hardware store and get some wing nuts because the wing nuts that were on this had rotted. Yeah, metal rot. It was weird. Okay. All right. 4 cases. All right. Excuse me. 4 cases. First 3 cases are when a real image is produced. The last case is when you get a virtual image. I'm going to do the first and third case, the 4th case, and then I'll do convex mirror to show you how that works. Okay, so here we have an object. It's a candle, all right? And I'm using candle because, well, if it wasn't lit, you could still see it in the mirror because there might be another light source that's giving off light. It bounces off the candle, diffuse reflection. Some of that light goes to the mirror and gets reflected in a predictable pattern. Okay? So, from any given point on the candle, at least 2 rays of importance are coming out from it and interacting with the mirror. This is a spherical concave mirror. The dashed lines on the back side of it represent, that's the side that's not reflective. So the front side here, the inside of the bowl, if you will, is the reflective side. Okay, so I'm going to use the point right here that represents where the wick is next to the candle and the bottom of the candle flame. That is going to be the point that I'm going to look for where the mirror is reproducing the image. Okay? So, first line, you draw from the object to the mirror, and it has to be parallel to the principal axis. Okay? You see what I've done? Now, yes, you put your ruler down just like so, and you draw your line across. It's hard for me to do that right on this easel and not block everything from you, okay? And so that's why there was the interruption there, all right? Now, when this ray goes over here, due to the geometry of the curved surface, the normal line is going to be right about there, and so the reflection that happens off of it follows a predictable pattern. It reflects through the focus point, F over here. Okay, so right there, that's my reflection. That's my reflected ray. In the instruction sheet, that would be a dotted line. That's one of the dotted lines there. Okay, now, from the same point on the object, another light ray that represents that point on the object, because this is a diffuse reflector, Another light ray is coming out and passing through the focus point. Interestingly enough, the other way you could think about this is the spherical wave front that's going out from this. And part of the spherical wave front is parallel to the principal axis. And the other part of the wave front is at this point, it's passing through on the way here. Well, once it gets here, that's part of the spherical wave front gets reflected parallel. Either way, if you're thinking of it as a ray, the way Isaac Newton did, or if you're thinking of it as a sphere, the way Victor Huygens did, then it will reflect back to the same point. So there you see the second ray, second part of the spherical wavefront, if you will, goes through the focus point on the way to the mirror. Now notice it's really low down there. Okay? All right? That gets reflected back through parallel to the principal axis. Okay, now I know it's a little difficult to see because it's a little far away, but you see how I've drawn that parallel to the principal axis? Now, up close, here's what you're looking at. Okay, you see we've got the one coming out parallel to the principal axis, and it gets reflected back through the focus point, comes off here into space. We have the second one, goes down through the focus point, gets reflected back, and notice right there, we have an intersection point of the two rays, two reflected rays, that represent that point on the object, meaning that at this point in real space, I could put a piece of paper, I could put my finger, or if I look exactly that far into the mirror, I mean, just you'd see it automatically. You'd see a small image. Why? Because think about it. What does that point represent? It represents where the wick is attached to the candle. If I were to redraw lines for every part of this candle right here, I could replicate all of those intersections in that space right in there. Okay? And so my image looks like a flipped over candle. I know it's hard to see over there. I know that that's kind of hard to see that it's a flipped over candle. But that's what I drew there. Okay? And that's why on your worksheet it uses arrows. Arrows are to see, they're good for seeing when it's right side up or right side down. Okay? So this is case one. Case one, when an object is far beyond the center of curvature, the image will appear at a location between the center of curvature and the focus point. The farther the object is away from the center of curvature, the closer the image will appear to the focus point. The image will always be inverted. The image will always be smaller, and it's a real image because of that. Not because it's smaller, but because it's inverted. It's also a real image because it appears out here in real space. All right, let's reverse this. Let's, instead of having the object out here beyond the center of curvature, let's have the object inside the center of curvature. Okay, here we go. Case three, not two, case three, when the object is between the center of curvature and the focus point. And I've kind of put it close to the focus point to make a dramatic representation of what we're going here. Same rules still apply. I'm going to draw my first ray of light as if it were passing parallel to the principal axis on the way to the mirror, and it will reflect back through the focus point. My second ray of light from the same point on the object is going to pass through the focus point on the way to the mirror and reflect back parallel to the principal axis. So here we go. Okay, there we are. First ray parallel to the principal axis. And I've drawn it so that the reflected ray passes through the focus on the way away from the mirror. That's the geometry of the situation. There. All right, my second ray coming from the same point on the candle as the first ray, because it represents the same information, goes through the focus point on its way to the mirror. It gets reflected back parallel to the principal axis. Okay, you see how the two reflected rays intersect? And they intersect out here in real space compared to the mirror. And that represents that point on the candle where the wick is extending from the body of the candle. So if I had drawn a lot more points from a lot more lines from a lot more points on the candle, it would reproduce an image of the candle that looks like, okay, it looks like that. It looks like the inverted candle. And you can see it's a lot more obvious with this case than it was with the previous one. All right, so this is our object, the original candle. This is our image. If I put a sheet of paper out here in real space, that's where it would appear. If we had been doing this in class, I have reflectors that I can show you how this would actually work. Now, this is the way that you would use this for a flashlight or a headlight. You put the light right here at the focus, and all of the light that's going this way away from that light bulb will get reflected back, and it would form a parallel, nice, straight, intense beam going out from here. So you can use a relatively small bulb, but because it's collecting the light and all of that would normally just be going out into space over here, it's reflecting it, and it's reflecting it all parallel. And so that's why this application of the reflector is when you have a light bulb here or something like that. You can also use this to create directional reflections of sound waves. If you were to stand right here, anybody out here would be able to hear you and hear you clearly, even if you whispered. Because your whisper, all of that energy is going out like this, but anything that encounters this reflector, boom, it's getting reflected parallel to the principal axis. And so anybody standing out here would be able to hear what you're saying right here. Okay? This is also true of satellite antennas. This is where the antenna actually is, and it sends its microwaves out to here, and that beams them directionally where they need it to go. All right, and so that's how this reflector can be used. You take a small object right here, and it produces a large image way out here in real space. Okay, now for the fourth case for a convex mirror, or concave mirror, excuse me. Okay, case 4, an object inside the focus point. Okay, first ray, parallel to the principal axis on its way into the mirror. And that ray gets reflected back through the focus point. Now, is there any way that I could start drawing a ray from that point on the the candle, have it go through the focus point before it hits the mirror. In other words, I couldn't draw it like that, right? It just wouldn't make sense because it would never hit the mirror. So I'm going to draw a ray off of that as if it could have passed through the mirror on the way to the candle and then away from the candle. All right. That's how we have to do it. And as you can already see, since you can't get it through the focus on the way to the mirror, it's going to be doing something weird. Okay, so you can see that I've got this kind of dotted line from the focus point up to the candle that represents how that ray kind of virtually starts at the focus point on the way to the mirror, and then at the mirror, coming, obviously coming from the object to the mirror, it's going to get reflected back parallel to the principal axis. See that? Okay. But look, is there any place on the actual, the object side of the mirror where that ray and that ray are going to intersect? Nope. But there is a place where they virtually intersect. All right. We have to extend each of the reflected rays back into the mirror. Okay, you can see I extended this one up and this one straight back. And notice where the two dotted lines intersect. That represents that part of the object where the light rays virtually are intersecting behind the mirror. You can't make a virtual image out over here. You could never put a piece of paper behind the mirror and see this image. You always have to be looking into the mirror to see this image. Okay? That's why this is a virtual image. Okay, so you've got the rules, and I'm going to be sending out a worksheet that I want you to reproduce those each of the cases on. Okay, print yourself out a second one if you want, and practice using those rules, and make sure that you get the following qualities for each of your images for the four cases and for the convex lens. Okay, for the first case, when the object is beyond the center of curvature, when it's at infinity compared to the focal length, compared to the center of curvature, when it's very far beyond the center of curvature, the image will appear between the center of curvature and the focus point, between F and C. Okay? The farther away it is, the closer to F it will be. It will be a smaller image than the object is. All right? And it will be inverted, meaning that it will be a real image. Case 2 is rarely ever happens with mirrors, but we're going to do case 2 because it has a very practical application with lenses, and so getting us familiar with this case is important. Case 2, the object is at the center of curvature. In other words, it is twice the distance that the focus is from the mirror. Okay, so at the center of curvature, the image appears at the center of curvature, below the object. Okay, the image appears the same size as the object, and the image will be inverted. It'll be real. For case 3, when an object is between the focus point and the center of curvature, the image is going to appear out beyond the center of curvature. Okay, and this is when you're using to take a small object and make a real big image out in space, out in real where we are. Okay, that's what I mean by out in space. The closer the object is to the focus point, the closer it will appear at infinity. Okay, infinity could be a couple of 100 meters if the mirror and the object are centimeters in distance. Okay, the image will always appear larger, and the image will always be inverted. Therefore, it's a real image. Case 4. Case 4 is when the object is inside the focus point, okay? Or in other words, it's between the focus length and the mirror, all right? The application for this is dentist's mirrors. Dentist mirrors, when they put them into your mouth and they are looking at your teeth, they actually have a concave, uh, a slight concavity to them, which makes the image of the tooth that they're looking at in the mirror bigger. And so it magnifies any defects that might be in the tooth. It magnifies any place where there might be some of that dye that they use to find plaque buildup so that they can see it and take it out. Okay, so because of that, the image will always appear inside the mirror. That's the only way you're going to see it, is to look in the mirror to see it. It can't be projected out onto a screen out here in real world. Okay, the image will always appear larger, advantage to the dentist. Okay, and the image will appear upright so that they don't have to worry about going backwards to it. Okay, it will always be able to move in the same way. It'll be a virtual image. The last one is the convex mirror. Convex mirror, there's only one case for it. Convex mirror is a wide angle view, and because of that, it always distorts the image and makes it smaller. The image will always be upright. The only way to see an image in a convex mirror is to look into it. These are the security mirrors that are in stores. These are the security mirrors that might be at an angle in a roadway so that people can see around the corners. These are the right side view mirror on your car. All right, they are curved so that the reflecting surface is on the outside of the rounded side. Okay, you can only get virtual images with a concave mirror or convex mirror, excuse me. And they always make things appear smaller, which is why on the mirror there's always that warning: objects are closer than they appear. That magnification or demagnification that is created by the convex surface is what makes us think it's farther away, because one of the ways our eyes perceives distance is relative size compared to other objects. Okay, so we look in the side view mirror, cars appear smaller than they are looking like in the regular mirror. If you're just using the side view mirror, you're often thinking that you have more room than you normally would. Okay, that's why you always double check when you're using it. Look to see if something's there, and then look to see where it actually is. Okay, thank you very much. This has been Geometric Optics Curved Mirrors with your friendly heavy physics teacher. And of course, as you know at this point, I won't be seeing you again in person in the classroom before the end of the school year. I miss you guys a lot. Have fun.